This image depicts the three areas in which the three curves were chosen from. Area number 1 is along Centerville, area number 2 is along Uniontown, and area number 3 is along Bull Run Regional Park.
Alright, so these three circles that are depicted here are the curves that we fit into the area of study that was shown on the previous slide. So the first one all the way to the left has a radius of 0.929 miles, which is equal to 1,495 meters. The second curve has a radius of 1.886 miles, which is equal to 3,035 meters, and the third curve has a radius of exactly 1 mile, which is equal to 1,609 meters.
The displacement before the first curve was measured by finding the straight distance from the curve to the Dunn-Loring metro station, which was shown to be 18.59 kilometers. Then, using dimensional analysis, this value was converted to meters, which was 18,540.
The displacement before curve number 2 was calculated by first determining the number of kilometers along the line, which is 21.84 kilometers. Then we multiply that number by 1,000 meters in order to convert the number to 21,840 meters.
The displacement before the third curve was found using the same methods as previously described, which is 25.98 in kilometers and 25,980 in meters.
The area surrounding the first curve includes a cluster of private homes to the left of the road and the Meadows condominium to the right. Since this is a highly inhabited area, more attention should be paid on building the sound walls to the embankments so that the noise is reduced to a minimum for the residents. The second curve is adjacent to a large grassland area to the left and a wildlife conservation park and a park for special events and festivities to the right. The third curve is near individual stores, hotels, and restaurants, so in constructing a banked road, we have to be conscious of minimizing the sounds to not affect these businesses.
Geographically, the cars driving along all three curves are heading either west or east depending on one's reference frame. If heading west, for example, cars along all three I-66 curves are on I-66 westbound driving on eastbound lanes. The cars depicted in the picture to the right, for example, are along curve number 1 and are heading west near Centerville, Virginia. In terms of curve number 1, the number of lanes is generally 3 heading in the west direction and 3 heading in the east direction. The pavement is asphalt with the exception of exits 57 through 64, which previously had deteriorated concrete but are now covered in 4-inch asphalt. In terms of curve number 2 and curve number 3, both of the number of lanes are generally 4 heading in the west direction and 4 heading in the east direction. Furthermore, the pavement type is asphalt for both of these curves.
So we calculated the banking angles for each curve using the maximum velocity of 65 miles per hour plus 20%, which is equal to 78 miles per hour or 34.87 meters per second. And so from that, we found for the first curve, the ideal banking angle would be 4.74 degrees. For the second curve, it would be 2.34 degrees. And for the third curve, it would be 4.41 degrees. And you can see the curves' respective locations on the map. Alright, so this table is a compilation of all of our calculations for each curve. So using the radius, banking angle, and coefficient of friction for dry roads, wet roads, and icy roads, we found the maximum velocity, and comparing these maximum velocities on the dry roads to the 78 miles per hour or 34.87 meters per second, we found the percent increase for the margin of safety. So for the first curve, the margin of safety would be 290.4%. For the second curve, it would be 413.8%, and for the third curve, it would be 301.3%. So over here we have our percent increase calculations. So these were found with the new velocity of the maximum velocity on the dry roads minus the initial velocity, which was 34.87 meters per second for all three of them, and divided that by the original velocity, multiplying the entire thing by 100, and that gave us the percentage, the percent increase. And then next to that, we have our velocity without the banking angle. So basically, that was just found doing the velocity squared equals the coefficient of friction times gravity times the radius, and we did that for all three circles. This value was what was added to 34.85, which was the velocity with the banking angles, and that the sum of those two gave us the value for the maximum velocity for each surface and with the banking angle. All right, so now I'm just going to walk through some of our calculations for how we found the banking angles and the velocities for each curve. So for the banking angle, we found the banking angle using the formula tan theta equals velocity squared over gravity times radius. So to find the angle, we kept the velocity constant at the maximum velocity for this area, which was 65 miles per hour plus 20%, which is equal to 34.87 meters per second. So using this, we squared 34.87 meters per second and divided it by 9.8 meters per second squared times the radius of each respective circle. And then we did the inverse tangent of that value to find the banking angle in degrees. So next, using this banking angle, we plugged each angle into the formula, this formula rearranged, which is velocity equals the square root of the tangent of theta times gravity times the radius. And from that, we got the velocity to be 34.85 meters per second, and that remained the same for all three curves, given the respective banking angle times the radius. The changes in those accounted for the difference. So that number, 34.85 meters per second, was added to the velocity of each curve found with the respective coefficient of friction for a dry surface, a wet surface, and an icy surface. And so to find that, the coefficient of friction we used for dry surfaces was 0.7, for wet surfaces was 0.4, and for icy surfaces it was 0.1. And so in order to account for that coefficient of friction and find the velocity with that, we did velocity equals the square root of the coefficient of friction times gravity times the radius, and added all of those values to 34.85 meters per second, which is the velocity with the banking angle for each curve.
For our suggested improvements for I-66, our first one is to elevate the sound walls by approximately 1.5 meters, since the banking angles will raise one side of the road so that the sound walls will need to be elevated as well in order to be effective. Our next one is to add an extra lane in the interior to decrease the volume of traffic and distribute the cars over a greater surface area. Lastly, eminent domain laws will need to be exercised to seize all the private property that the cars will cover, as mentioned in the topography section, which includes parks, condos, buildings, and lands.
So because the curvature of these curves are circular, there is a centripetal force present that keeps the car moving in circular motion. So on the banked angle curves, the centripetal force is provided by the frictional force in between the car's tires and the surface of the road.
The motion of a car as it encounters different road conditions and turns can be described by the forces acting on that car. There are generally four relevant classes of forces: the normal force supplied by the road, the force due to gravity, the force supplied by the car, and the force of friction. On a straight, level road, since there is clearly no vertical component for acceleration, the vertical component of the forces must cancel out. However, it is possible for the car to initially move forward if the force supplied by the car overpowers the maximum force of static friction. Once in motion, the force supplied by the car must equate to the force of kinetic friction in order to maintain a constant velocity, must overpower the force of kinetic friction in order to accelerate, or underpower the force of kinetic friction in order to decelerate. In the image depicted, the force of gravity is pulling the car downward. The normal force is pointing upward beyond the vehicle, and the normal force in the x and y direction are depicted according to a typical x and y direction on a plane. On a banked curve, the force of normal contributes to the horizontal component of movement, and therefore contributes to the centripetal force. This additional component to the centripetal force allows for a stronger force to keep a cart in circular motion. This in turn maintains the direction of the cart in case of dangerous weather conditions.